wish it was sooner, but I can't help it. All right, so back to material in hand, and by the way, I will be covering, what I'm covering today will be on test 2 and the final, so to motivate you a little bit. Just to remind you, we were talking about entropy, and sorry, I'm kind of not the name of you up there, right? Yeah, I see you. I know who you are now because actually, when I was taking up your test, I was looking at your names. That's how I learned your names, by the way. So now I know who most of you are. So entropy is defined, sorry, the change in entropy, the change in entropy is defined as the heat transaction divided by the temperature. And we can then do tricks with this, as you saw last time. I just want to remind you that we can insert work. Anyway, there's tricks. You saw them. I'm working backward because I'm out of it, because we're working on grants. And we get to this equation for the change in entropy. Now remember, this is universal. It applies to all the 4 conditions that you labor under: isothermal, adiabatic, reversible, irreversible. This works for every one of them. There you go. Obviously for isothermal, this one, even if I've seen people on test 2 and on the final plug in numbers for this term on isothermal. That's kind of dumb. It's a bit of a waste of time, but it's okay because you got the number 0, right? And natural log is 1. And then they did that part right and got full credit. Great. All right. And of course, if you're adiabatic, you're going to see a change in volume and a change in temperature. So anyway, that works. Just to remind you, okay, then the thing we covered right at the end of, what was that? Last Monday. I was kind of babbling then. So I don't think you're going to remember, and I was kind of screwing it up. I was talking about the other statement, the more important statement of the second law, which is that entropy increases in a spontaneous process. Sorry, I hate just writing stuff out. Okay, now I have to qualify that a little bit because you probably have heard this at one point. You've heard that entropy increases or stays the same in a spontaneous process, and I've already screwed up. I've already screwed this up, sorry. I need to, see, this is how you hear about it on the news or something, you know. Total. Sorry about that, second one. Total entropy increases in a spontaneous process. Now, I choose to define it this way. I don't like this definition because, again, you've heard total entropy increases or stays the same in a spontaneous process. Stays the same. Let me define that. Hang on, let me write this down. So, change in total equals 0. I don't like, for the purposes of this class, I don't want to define that as spontaneous. This is equilibrium. It's the definition of equilibrium, by the way, when something minus something, right, after minus initial, final minus initial, is 0, and that thing, of course, is total entropy. Total entropy final minus total entropy 0 for that process is technically an equilibrium process. So whenever you hear total entropy increases or stays the same in a spontaneous process, stays the same means that they're lumping in equilibrium with spontaneous, which I personally agree with, but I think that would actually not help you understand this for the purposes of this class. So I tend to define this way, and I have this kind of corollary that says that, oh, by the way, in case you get an entropy change of 0, then that's just an equilibrium process. Which, by the way, we didn't cover this last time, but I know I'm babbling, which is a reversible process as well. So it's kind of a funky thing because now let's do a reversible expansion. Again, I'm pushing on the magic cylinder, and remember that I keep letting up on the pressure such that my push and its pull are basically equal. Right, that's a very slow let go of the pressure versus to just stand aside and jump away as the magic cylinder expands. Technically, see, that's the thing. Reversibly, I'm in equilibrium because I'm always just letting go a little bit. So technically, we're equal with just such a small differential that it doesn't matter. So that technically was an equilibrium process, and that's why big picture, you get more work out of the system, right? That's the most reversible work, it's the most negative work, it's technically in equilibrium. And Carnot cycle, you find that total entropy change is 0, it's the most efficient. Just reminds you of all the things I've already said. Okay, so now as I mentioned before, now we've got to figure out how to calculate the total entropy. Now this is the part that's on the second test and on the final. This is another one of those 48 characters I can now introduce into a gas expands, a gas contracts. So the total entropy change will be the system, right? And remember, I leave no qualifiers on the S. It's just S. Whenever I say S or P or V, it's the system. In fact, I never emphasized, maybe I've emphasized that once or twice when it came to pressure, but anyway, I've not emphasized that. I've always been telling you we're going to calculate this and that. What did not come out of my mouth is on the system, because I knew you would just assume that. Now this is where this gets to be a bit of a biz knocker. For the first time, I will do a calculation on the thing that happens to the outside of the magic cylinder, not just the inside as well as the outside when it comes to entropy. So again, assume that that's the system as you have been, but now you have to do surroundings, which I'll just put SURR anyway. Okay, so again, magic cylinder question, test 2, final. Gas expands, gas contracts. Tell me the entropy, total entropy, and surrounding changes in entropy. All right, it's totally on there. So let's break it down. Now, okay, I've got my reversible defined. Reversible. Oh no, okay, I did spell it right. Sorry. And by the way, you see, this is why I actually want to keep this equilibrium and the spontaneous. Why I want to separate them is for this reason alone. It's because I want you to remember that, again, for the purposes of this class, change of total S of 0 is equilibrium, which means reversible, and that if it increases, that process would technically be irreversible. And that's, again, I'm defining it this way, which is a little odd, because I think it's going to help you answer these questions. Formally, it's not really that good to define it that way, but whatever. Let's just get through this class, all right? Just get through the day. Okay, so, all right, I've got this defined, which should not be too particularly terrible. And I tell you what, blah, 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 blah. Again, I'm a little out of it. Let's, nuts and bolts, let's just get through the class. Let's define the 4 conditions, right? And we'll start with isothermal and reversible. Okay, now again, memorize as little as possible, but I am asking you on the test. You've got to answer. Let's be practical. Let's think about the ways to get this as fast as possible, accurately. That way you move on to that derivation question where you ignore the equations that I wrote. So, isothermal, reversible, what's this? 0. Don't forget units. There's a point on the test. You didn't have units, just a point, it's not a big deal. Okay, so now this would get a star because this is the definition of reversibility. Okay, now you've got, now I'm asking you for the surroundings. Again, I'll abbreviate it that way. And now you know that's minus the system, right? Which, of course, is minus the change in heat versus temperature. Now the point of this is to understand, why do I need to worry about the total, and why is there a total to worry about? What doesn't everything happen in the system? Well, so again, I did cover this last time, but I just really was worried about the test myself. The way that the surroundings entropy change is by the heat transaction. And for the purposes of this class, we'll just only define it by the heat transaction. So it kind of makes sense. If I have the magic cylinder and I'm pressing on it incredibly hard and we're isothermal, that thing got impossibly hot, right? Remember, you're allowed to think of very extreme situations. And in this case, the magic cylinder, I compressed on it till it was white hot. And that heat, because I'm isothermal, comes out into the world. And the world, of course, has gotten hotter. And by the definition of changes of entropy, the world's entropy has increased. So that is part of the total, right? So that's what I'm seeing right here, is that heat transition affected the outside entropy. Now remember that there's a corresponding change, which I am allowed to pull the magic cylinder open or expand it. You know the gas will get cold, but I've already said I'm isothermal, so the outside entropy has to provide heat, which causes it to freeze, which is a loss in entropy. So that's again, yeah, that's why that is. Okay, now, and then of course we define this as above. Pretty simple. Next one. Now this is the tricky one, by the way. Isothermal irreversible. What's wrong with me? Okay, let me get a new pen because this is dying on me. Okay, this is the one that will cost you a point because it's the tricky one. And let me show you why it's tricky. It's because it's indeterminate. We're talking about this statement of the second law. Here, let me say that the total entropy plus the surroundings, which is equal to the total. Okay, by definition, is simply greater than 0 than 100 units. Okay, so here's the problem. All right, for one, I've said, hey, what's the total entropy change for this isothermal irreversible process? Okay, that's basically the second law of thermodynamics, so you should remember that, especially I asked it on the final. So we've got that, but now, all right, so you've got 1 point. You've calculated this thing, which again is just NRLNDF over VI, but now you're stuck with this. Now this is again the tricky one. I said that this is the one you'll most likely lose a point on. All right, if you solve this sucker, you get this. And so this is the kind of thing I would not put in a cheat sheet. I'll put this like in a cheat sheet, but I won't put this. Because you should be able to figure it out. I mean, that's what I need you to show me you can figure stuff out. Okay, so the surroundings is greater, the change in the entropy of the surroundings is greater than minus the change in entropy of the system, again defined as NRLNDF over VI. And that's it. That's the answer. Right? So again, the thing that's tricky about this is that you can't actually give me a number. You can say, well, it's at least this or more, but you can't pinpoint it. You know, well, it's at least 5 joules per K, maybe it's 6, maybe it's 7, but you can never give me an exact answer. And I think part of the reason is because, okay, let's do, let's see, okay, we lose, okay, compress a cylinder. Compress a cylinder means a loss of entropy, and we're still isothermal, right? That makes sense because there's less volume and isothermal, so that didn't change anything. But what pushed it? What pushed it so suddenly, right? Because this is irreversible. Was it a cat? Because my kitten is going nuts, and so she knocks stuff over all the time. And I can imagine if I had my cat push on the magic cylinder, that cat is just an entropy generator. So you don't really know what's happening on the outside such to instigate this transition to begin with. And that thing, especially if it's Charlie the kitten, is horrifically entropy generating. So that's why, in my opinion, you can't really know what this is. Now, again, let's do a little practice problem because this can be kind of tricky. Let's say, never forgetting the conditions that we're working under, let's say that you calculate entropy change, and again, I'm just going to call it this so you know that I'm doing the system. If, let's say that it decreases by -5 joules per K. I don't know why I put a little. Now, of course, you've already said that the total is greater than 0, so you got your point there. But I also asked you this. What is it? Greater than 5. Greater than 5. Right. Okay, for one, I'm not giving you this formula. You should be able to figure it out from this, but you need to memorize it to star. Okay, but you just can't do this. Okay, you're at the test, and you see this in the cheat sheet, but you're blind. Okay, here's how you think your way around it. So now you had to have gotten here, or you're already dead. All right, so you had to have done this, and now you need to figure this out, but you're just not going to do it this way. Here's how you think your way around it. you've got to wipe this out. Remember, this is an entropy deficit. It's got to be overcome, it's got to be negated, and then you've got to pick up a little bit more, right? So you've got to have +5 to get that to 0, and then add a little smidgen bit more on top of that. Otherwise, you're not spontaneous and irreversible. Okay, not bad. Let's do this. Now, is greater than -5 for the exact same reason. Okay, so now this is why this one's a little funky. So this is the magic cylinder was expanded by my cat pulling on a string that pulled the plunger. What can happen is that the outside can actually lose some heat. So remember, the magic cylinder expanded, it got cold, but then the outside warmed it, means that it lost some entropy. And so it lost at least this much, and plus a little bit positive more, right? So it can lose, but it just can't lose too much, because if it loses too much, the total is less than 0, which can never happen. So anyway, again, formulas, if that's the way you do it, or plug it in your calculator perhaps, don't let me catch you, or logically just walk your way through it, either way you'll get the right answer. And then, yeah, I don't have anything else to say about that. Okay, next one, adiabatic, no, we'll do reversible. This one's easy. Okay. What is it? Right, 0. Remember, that's by definition. It does not matter. I said reversible. That dictates everything. And okay, now this is where this gets kind of funky. So we got the entropy of the system plus the entropy of the surroundings equals the entropy of the total, which I define as 0. Okay, what's the entropy of the surroundings? Remember that we only change entropy of the surroundings by heat transaction. So what is it? It's what? Sorry, I just forgot my email. Okay, again, this is wrapped in glass wool. There's no heat transaction. What's the entropy change of the outside? Right. And therefore?
0.
Right, 0. So I didn't tell you this yet. I'll have you do it on some calculation. My formula up there on top for the change in entropy of an adiabatic reversible process. Now, anyway, when you solve for an adiabatic reversible process and you have that adiabatic equation of state and yada, 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 you plug in your final volumes, your final temperatures, it will naturally come out to be 0. Remember, that equation works all the time. So just remember, if you solve your adiabatic reversible equation, all the P's and B's and T's, and you plug them into that equation up there, which is fine, you will get the number 0. Or you could just write this out and I'll understand that you understand, that you know what you're doing. Okay, so everything's 0. And now last is adiabatic irreversible. And this case, and I will have you do one of these one last time, so let me write it out the same way I did a minute ago. So again, the total is system plus surroundings. Okay, now the surroundings, again, is adiabatic. Right, is still 0. I'll remember my units. All right, the total is, it's not 0. Right. This is all I have left. Yeah, the total will just simply be the change in entropy of the system. The change in entropy of the system will not be 0. Now remember, the entropy change of, here, let me toss this up here. The entropy change in adiabatic reversible, everything is 0. Because for one, this equation is going to make the interior 0. The total is 0 by definition, and so therefore the surrounding is 0, but I already do that because there's no heat transaction. See, no matter which way you think about it, 0, 0, 0. Okay, adiabatic irreversible, you calculate your final T, your final V, which remember was a nightmare. You plug it into this equation, it will be small but finite positive. And given that the outside didn't really do anything, the total is just the interior. And again, you've solved your adiabatic minus P exterior dV is equal to C dVt. You solve that giant ass thing, you get your parameters, you plug it in here, you get like, it's going to be like 1 joule per K or less. and that's your total. So there you go. That's really all I've got. So nuts and bolts on entropy. Are you set? Because I want to switch directions here. You're set. Okay, so as much as entropy, this is a crazy thing I never could get over. Entropy has this one formula, but it ends up being a little bit more complicated. I mean, it's not terrible, and you don't, as in all times, I try to give you ways to figure this out without memorizing a bunch of stuff. I hopefully I've accomplished that. You've accomplished that as well. So regardless, simple formula, yes, look at this, 2 whole boards of complexity, which is kind of blows. Let me summarize the second law. Now remember, second law says you can't turn all heat to work. And if I ask you what's the second law on the final, which I'm prone to do that like every other year, you can say you can't turn all heat to work, which is totally fine. You should stop right there because that's the answer. Although it is equivalent to state that entropy of a spontaneous process increases and at equilibrium it stays the same. Now, here's what I want to emphasize in this. I'm just going to write that down because this is kind of the most important way to write the second law. And by the way, what is important about equilibrium, here I'll write that one down, is that we're going to figure out a way to calculate entropy, total entropy, via delta G, by the way. So when you were taught in freshman and hopefully high school that delta G of 0 is when a process is at equilibrium, you weren't actually calculating the total entropy. It was a mask, and we're going to cover that in about a week. Okay, anyway, what's good about calculating total entropy of 0, again, it can be done. You actually figure out when the chemical process stops, allowing you to calculate the yield of the reaction, which you are doing in about a month. So that's probably one of the more interesting things. Okay, spontaneous is greater than 0, and again, units, because I'm counting off if you don't have them. Greater than 0, what about less than 0? When does the entropy change? What kind of process occurs for which the total entropy change is less than 0 or negative? Call it something. Now, of all the processes I've been talking about, I never... What was that?
Compression.
None of them. Nothing. Well, wave a magic wand. Does not happen. That's a trick question, so sorry.
Nice.
Yeah, I like trick questions. Anyway, does not happen. There is no process for which the total entropy is decreased. It simply cannot occur. At best, things can be at equilibrium or they fall apart, right? Just like your lives. So, you should see how thick my grant is. It's like this thick, by the way. I had to write all of it myself. So, okay, so again, entropy for you. But now the thing I want to cover, which is actually a grad level concept, but I want to cover it because it's kind of neat. And it actually, I always teach this class with the idea that you all may enter grad school in chemistry because, I mean, it's reasonable of me to do so. We've had an upswing in applications from UIC. Probably about 5 of you will actually go to grad school, which is higher than it's ever been, which is pretty good. So I need to make sure that you can go to grad school and not fall on your ass. Also, I don't know what's on the MCAT, all right? I seriously don't know. I'm guessing that this could be on the MCAT. Again, I really don't know, but I feel like maybe I should cover it just in case it is. Which is, what is entropy actually? Remember, that everything I've been talking about, see this delta or my little delta, my partial, that's change in entropy. But entropy is exact. The change in entropy is exact. And therefore, obviously, I have formulas for the change in entropy, but I should have a formula for entropy itself. The thing that I take the derivative of with respect to volume and temperature and get all that jazz. Okay, so what is that? Now, the emphasis here is that entropy is what you've been told before, that it's like the degree of chaos. You know, entropy represents chaos, it represents randomness, which is because the reason we have this concept is that I think about a balloon and it's full of gas. It'd be always about a centimole, which is the number I always use when I do a balloon. And I'm just kind of looking at the balloon, I'm looking at the molecules, And the thing is that all those molecules are moving kind of like billiard balls, and I know that a computer can solve the motion with decent enough accuracy. Of course, it would be off after enough simulation time, butterfly effect and all that jazz. But for the most part, if I have a balloon full of gas and I look at the gas molecules, where they're at and where they're going, I can reasonably predict their behavior for a pretty long period of time. So where's the entropy? The problem is that I can't actually do that. For a simple balloon, the biggest supercomputer on the Earth could not simulate the gas in a simple balloon because there are just too many gas molecules. And that will probably always be true. I don't care how big our computers can get. Quantum computers, we can never simulate a simple balloon. Instead, I can either give up and say, well, I won't even try to understand a balloon, and therefore I will never have machines like cars and power plants and nuclear weapons. So instead, what I do is I look at all that chaotic behavior and I decide it's just that. It's chaotic random behavior, and the dangerous thing is mathematicians have given us ways to analyze things that are chaotic and random, which is the science of, begins with a P, and it sounds like probability. Probability, right. So instead of trying to get a supercomputer to look at this balloon of gas deterministically, instead I can look at it as a chaotic bunch of bees and analyze its properties with probability, which is actually entropy. And again, that's because it's so chaotic and random. So anyway, that's motivation for this. Okay, so what I really want to do is figure out not what the change of S is, but S itself. Now remember, I have not written the letter S without a delta in front of it. I have not done that because I have not defined the function. Yet I know that I should be able to define the function because the change is a state function. The change is exact, and therefore S is a state function and it should be defined. Just like I defined U via the equal partition theorem, and I defined H as U plus PV, it's all defined, as well as the changes. Okay, so what is this? All right, now I'm going to start out with this. I'm going to start calling it a function of this thing called rho. I'm going to figure out what the function is in a minute. I got to define rho. Rho is the degree. It has two definitions: degree of randomness. Sorry, my handwriting's a little off today. Or number of states. And these are the same thing. You can think of like, if something can exist in a large number of states, its behavior would be kind of more random, right? Something that can't move is not random because it's not moving, it's not doing anything, but that's because it lives in only one state. This should be confusing, by the way. If you're looking at this like, what? You should be doing that because this is a very difficult concept to understand. But I'm going to explain it with simple models, and then we'll do harder things in a minute. Let me do a simple model to understand what rho is. And once we understand what rho is, we'll get the function which defines entropy. And to do that, what I'm going to do is I'm going to create a box with 3 gas molecules. And the gas molecules can be in one of 3 different states. Let's say it's A, B, and C. Here, I'll write that up here. This isn't really important, but I just want to emphasize that there are 3 different states, A, B, and C. So maybe this is like a gas molecule that's trans, gauche, or, anyway. Okay, so, and one of the molecules is here. And I've got another gas molecule. Of course, it's tumbling around, and this is like a little Tetris piece. And its state is there. And there's one other gas molecule. And for whatever reason, its state is here, the C box. Okay. Now, to understand rho, and I'm going to use the first statement, the degree of randomness. I need to tabulate the degree of randomness, and I need to use the language of probability for the reasons I just mentioned, because there's no other way to understand random behavior. Okay, to do this, for this box of these weird gases with these 3 states, each one's in a different state, what I would do is, again, look at the probability that they're in these states. And to do that, I would look at this one. We'll worry about these in a minute. Let's look at this one. What's the probability that's in state A? And let's say the states they're definable but equivalent. 1/3, right, exactly, right? Because that's state A is 1/3 of the possibilities. Okay, so that's like the flip of a three-headed coin. There were 3 possibilities, and this one ended up in state A. Okay, now, like if I flip a coin twice, let's say I flip a coin once and it's heads, which was 50-50. If I flip the coin again and I get heads, what's the probability of heads? 1/4, right? 1/4. Heads was 50-50. A second heads is 1/4 because there's 4 possibilities. Heads, 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 tails, tails, heads, tails, tails, right? 4 possibilities, I observed one of them. The probability was 1/4 or a half times a half. Okay, so this is the first coin flip, a three-headed coin. The probability was 1/3. What's the probability that this one is in state A and this one's in state B? 1/9, or in other words, 1/3 times 1/3, right? Just like 2 heads on 2 flips has a probability of 1/4. This guy being in A, this one being in B is 1/9 because it was 1 possibility out of 9 possible results, and of course the last one is also 1/3 or 1/27. Okay, so again, in order to assess the degree of randomness, one of the ways to define rho, I would say that that degree of randomness is 1 out of 27 because it's no different than flips of a coin, which is exactly correct. Now, there's another thing I need to note. So I'm defining rho, but there's something I have to do to define, to get entropy. It seems like I handle all this, but now I need to get the function, and now I've got entropy. And to do that, I'm going to take a second look at this box, and I'm going to note that entropy is a state function which is extensive. And I know that because of the units. Right? Remember, I keep emphasizing units. By the way, no unit section on the next test. So that's one time, you'll never see it again. But regardless, you can see why I emphasize units. Entropy must be extensive. And therefore, let me just say that entropy is F1 over 27. Okay, now let's look at this as like number of states, or the fact that entropy is size extensive. Okay, so entropy is size extensive means that I should be able to add up the entropy of every state. So in other words, this molecule has a certain entropy, which is F of its rho, which is 1/3. Okay? And yada, yada, yada. So each one, right? So again, the point is that entropy is a state function. It has to be size extensive. So I should be able to add up all the little micro entropies to equal the total. So, it's, just like I would add up energy or add up work like I did the Carnot cycle. So this has to work, but at the same time, this has to work. So again, remember, this is the total microstates, the total degrees of randomness, and therefore entropy is defined that way. But I'm also saying that entropy has to be size extensive, which means it has to be defined this way, and therefore 3f of 1/3 must equal f of 1 over 27. Now the question is, what function does that? Anyone want to take a hint? It's actually really quite familiar. I mean, that looks incredible. What function would possibly add? So the point is that basically the functions multiply and add and get the same thing. What function would do that? Yeah, natural logs. F is a natural log. Because natural logs have that mathematical functionality. ln of A plus ln B is ln A times B, right? Only natural logs do that. And so what Boltzmann did was he figured out that, here I'll write it down, entropy. I'll work a couple of problems here. Now again, I have to emphasize, this is grad school level, but what I'm going to do is give you problems like you'll see on the next problem set, which I'll post Wednesday. Remember your problem set free right now. What Boltzmann figured out when he wrote down the Boltzmann formula, I don't know that he called it the Boltzmann formula, that would be shockingly arrogant, but he might have, is that entropy is, I'm giving myself a little bit of room here, just notice that. Entropy is natural log of what we now call W, which is the number of microstates. Okay, notice I've kind of redefined rho here. I'm going to drop this degree of randomness thing. I'm going to drop it because I just used it. It's correct. I just used it to get you to understand how entropy works as a probability and how entropy is still size extensive, and that to have those two characteristics simultaneously, it has to be natural log. And then what I'm going to feed is the number of microstates. So forget that degree of randomness. Think of it as the number of microstates. Why? Because the problems I give you are going to be easy to calculate the number of microstates, and there you go. Now what's missing is, what are the units of natural log of number of microstates? Huh? Yeah, no units. Well, that's a problem because entropy has units of joules per K. So what we do is we multiply by units, and since I'm going to do this for molecules, I'm going to use the Boltzmann constant, and I bet some of you might have forgotten what that is, which is the gas constant. It's 8.314 joules per K mole. But again, I like to think of entropy. You notice I'm using the single molecule language. I'm going to keep doing that again because it's easy. And so I take R and I divide by Avogadro's number. And that's where Boltzmann constant comes from. It's R for a single molecule, whereas the R you've been R'ing so far has been for a mole of molecules, which kind of makes sense because I like to explain things in terms of a balloon. But now that I'm talking about single molecules, I need to redefine that as the R of a single molecule, which is the Boltzmann constant. And yeah, so anyway, there you go. And let's see, do I have any good examples? Yeah, I'm going to do one example, and that'll be all I have time for. And then next time, I'm going to give you a really complicated example to show you that this works. And you're actually going to calculate changes of entropy for a simple chemical reaction, which involves chess pieces on the chessboard. You can see why it's easy to define the number of microstates. And I'm going to do a little example problem right now, which again, you will be able to do. This, I'm basically giving you answers to your homework, although the problem you have will be slightly different. And again, while it's a graduate school concept, it's actually, I really want you to know that entropy does have an equation form. Unfortunately, it's horrifically complicated, except in simple cases of like chess pieces on a chessboard, and we're going to stick with that. When you go to grad school, like this Wednesday, I'm actually going to use this formula to calculate the Fermi energy of electrons in a metal. And that's because I can calculate the number of microstates of electrons in a metal, and that way I calculate its entropy. So that's for grad students. You guys, chessboards, all right? Let me actually simplify that further. I imagine that this is the exam, and I gave you this. Just kind of the same thing as before. And I got one particle. Okay, now, again, the particle is in a state, but I could imagine that it could be in any one of these states. I just arbitrarily just decided it was at the top spot. Sorry, I almost forgot the units. KBLM. Okay, so what do you think? Number of states? How many? You said it? 3. LM3. Okay, now this is, I bet some of you were thinking 1/3. The problem with that is that would give you a negative entropy, which doesn't make any sense. Remember, all these state variables, it seems like really rare that anything is less than 0. There's no 0 pressures, there's no negative pressures, there's no negative volumes, there's no negative entropies. There can be negative changes in entropies, but when it comes to all of these things that we calculate, if they're not a change, they can never be 0 or less. Now, I am using, again, I want to show you this to emphasize that these fractions, these probabilities, I really did this as a tool to convince you that entropy needs to be a natural log. But it was just that. It was a tool, it was easy, but it's not quite right. Again, then just so you got that it's a natural log. Now I'm doing it right, by the way. I don't quite know what kind of molecule exists in only 3 little holes, but if it did, I did successfully calculate the entropy. And I will give you some actually really good examples in the future. Now this is where it gets kind of difficult, and we'll end on time. I don't have your tests or homework anyway. So of course what I'm going to do is go to the case of 2. of two particles, and so I said I got two particles and three holes, and now you have to figure out the number of states, and it's just a matter of permutations. I kind of hate permutations myself, but in this case it's not that bad, like in all the cases I'll give you. What's the entropy? 3. Okay. What about the fact that there's two particles? Does that matter? No, it actually doesn't. And if any of you have my videos from last year, if you saved them, I actually completely screwed this up last year because I put a 2 in front of it, which is just dead wrong. So again, the reason is that, see, I'm tempted to multiply this 2 by 2 because of the size extensivity. But that would actually be wrong. I need to look at that first example of probabilities where I have defined, despite the fact that there's two particles, I have defined the number of microstates, and that's it. Okay, last example, as you can imagine, and then we're done. Okay, 3 holes and 3 particles. What's the entropy?
3.
Okay, all of you are wrong.
0.
0. Right. There's only one microstate. I can't rearrange the x's. By the way, some of you probably were thinking 3 because I could put this x here and that x here. That would be correct if the x's are different, if they were different colors, but they're not. So the fact that the x's are the same, like think about it. If you shrunk yourself down and look at a water molecule, could you really tell the difference between this water molecule and that water molecule? No, especially when they're moving around like bees. So in this case, because you can't really tell if they rearrange themselves, there's only one way. It's basically a perfect crystal. There's only one way for them to exist, and the natural log of 1 is 0. And by the way, you just proved the third law of thermodynamics. This is actually the third law of thermodynamics, that molecules in a perfect crystal, technically at 0 degrees K, have no entropy. But we'll cover that in about another week. So.